So, yeah, I'm talking about Instaparse. It's a parsing library for Clojure, as you just heard. By the end of this talk, you should be able to create your own parser and your own interpreter for a very small language, a small toy language that you should all be able to create and just whet your appetite into something a little bit more interesting. So, why do you want to do this? Well, firstly, it's cool. It's actually a lot of fun to play around with grammar programming. A lot of the time you've been doing stuff with as expressions, you've been doing stuff with functional programming, maybe you've done stuff in imperative grammar type of programming. Has a different feel to it, a different way of debugging and creating these things. Second is more of a wishy-washy kind of thing. It's an idea that we can create a new form of UI experience. Now, I think it's pretty much a topic on its own, so I won't go too far there, but I think UI is kind of stagnated since the introduction of the Macintosh in 1984, with a mouse and a GUI, and you enter things in, and you press, and you drag things around. I think there's a lot of things that could be expanded here, and I think that could be a cool way to look in, and you should look at some of the work from Raskins, if you can, there. And finally, this one is a bit of a cliche now, because you can, but I want to put a little spin on this cliche, in that I think, actually, you can do it. Because I think a lot of people here have a feeling that a compiler or a parser or an interpreter is something that's just beyond their capabilities, especially if they taught themselves, they didn't go to university, or they didn't do that course at university. And I'm here to show you that it's not magic, you can do it, and I think you should all be able to learn a little bit from that in the first place. So it all starts here with this guy. This is Noam Chomsky. He's a philosopher, social critic, linguist, political activist, an anarchist. He's a lot of things, but in our field we only really care about this one thing, which is his linguistic work. And specifically for language work, we care about this work he's done on formal grammars and the Chomsky hierarchy, which is this thing here. Now this is a little bit complex to look at, but the basic idea is a little set. The one at the top is every possible language that can be computed by a Turing machine, and the one at the bottom is a very small subset, it's of regular languages. We only care about these two here, the context-free languages and the regular languages. This is the only thing that Instaparse supports, and the only thing a sensible language really supports. I think the famous example of a language that doesn't fit in those two is C++, and no one wants to be C++. So this is a regular language. We probably know them a bit better as regular expressions. You've probably all written a regular expression, but if not, then it kind of looks like this. You have these two slashes, or in Clojure, it's slightly different syntax. You have the double quotes with a hash in front. And then you have this thing here, and before you panic, this is really simple. There's a finite state automata. You start where it starts, and you go down to the state. It's a circle. That's okay. We see an A. Then we know we've read a capital A, we go to the state B. We keep on going until we go A, B, C, until we get to this one with two circles. Two circles means an accepting state. If we end up our computation at an accepting state, that means we've matched that string. If we get any character that's not one of those ones there, then essentially we've gone into an implicit non-existing state and we've not accepted this thing, etc. So to recap, that's a starting thing. It's like an arrow from God saying, please start here. This is a transition. It takes a character, we've read that here. Every circle is a state. There's a special state for accepting. I did it in green because I think green is a very accepting color, but usually you only see two circles, so if you see it in literature. And there's also, there's naming. It's optional though, and I don't give a shit really about naming, so for the rest of these slides I won't have any more names on them. This is regular expressions. You probably all know something about regular expressions, but really they can be distilled into these three things. One is you match a string, okay. The other is you have this idea of an or, so it's going to be either A or B. Or you have this thing with a star, it's called a clean star. It can be a bit messy. It creates a lot of A's, any number. You can see A plus in some systems too, but that's the same as just having an A and an A star. It can be, say, in our string we have any number of A's, including none. So we can go quickly through some regexes and what they look like in a finite state machine and a finite state automata, the same thing. Do stop me if you have any questions or you're not following as it goes on now. So we start here, this is a starting state, we get an A, and then to represent either the B or C, we have two lines. And we can take either of these lines, and essentially you just think about it, I'm an ant, I've landed here, and I just keep on walking down these things. So if I get a B, I go to this one here, if I get a C, I go down to this one here, and both of these have a transition A, that takes me to an accepting state here. So that's how you represent this regex, A, B or C, or A. Now, if we want to have a repetition, then we just have a transition that points to the state itself. So if we have any number of A, we go around here, and then if we have any number of B, we go around here. There's a small bug in this finite state automata that I found out after I scanned it in and put it on my presentation, but that's not so important at this point. The idea is that, yeah, A, any number of A's, any number of B's, and AC, and when you finally got to there, you get your accepting state. So that's what a regex is. You probably all knew what a regex is, but maybe you didn't know it in this slightly more formal way. So what do we need to make a language? Well, we need grammar rules. These are what Chomsky kind of innovated on. It involves things that look a bit like this. So this thing here in the color is the grammar rule. The green thing is a non-terminal. This means if we see one of these, we haven't finished our computation. We can convert those green things into things on the right-hand side of the arrow. The arrow means we can convert it to that. So this says we take a non-terminal S, and we end up with an A. A is a terminal. If we only have terminals left, we can end there. So this we call a production rule. Every grammar has a number of production rules. They need to be starting with one, so you must have one non-terminal to begin with. You must keep applying until there are no more non-terminals left in your output. And with a regular expression, a regular grammar, there can only be one non-terminal on the right-hand side of one of your rules. It can be either on the left or the right, but it can't be in the middle. Which side it's going to be depends on what kind of regular language you're doing. It's not so important for us right now. So if you're not following that so well, here's an example. We have two grammar rules. We take S, that's a non-terminal. It's in green, so we know it's a non-terminal. We move to SA, so that means whenever you see an S, you can move to SA. There's a second rule, S to empty string. It's the same as in Clojure or Ruby Python, just having double quotes followed by double quotes, nothing in there. This can also be written as an OR, so S goes to SA or empty string. This is the same rule, it's kind of a matter of preference. I'm going to keep the one on the top because this way I can number them rule 1 and rule 2. If you're not following, that's okay. It will probably be a bit easier when you see it like this. So we start off with an S. We know this is like our starting thing. We need to make an expression in a language that our grammar represents. S, you can replace with one of these two rules, and we just choose to apply rule 1. It doesn't matter which one we choose, but rule 1 is more interesting than rule 2, so we have SA. Now we still have a string SA, but we now have another S to get rid of here. So we can apply our rule again to remove that S in this string, and then we get SA again, so we have SAA. It's getting a little bit boring applying rule 1 repeatedly, so this time we decide to apply rule 2, and we get the empty string, and that basically gets rid of the S. So we end up with AA. There are no non-terminals left in the string, so we're finished. AA is a string in this grammar. It's a valid language string. So basically this is saying that this grammar here is equivalent to this regex over here. This is just any number of A's, and that's it. Any other string is not valid in this grammar. Any other thing there. Any questions? Everyone following along? Cool. So I told you before that you could only have one non-terminal on the right. This leaves us with a problem with matching parentheses and brackets. If we were trying to do a programming language, we kind of want parentheses, we kind of want brackets, so it's kind of a problem, right? The reason why is because this would be the regex, right? You would have one bracket followed by an asterisk, which would be any number of opening brackets, and you can have a closing bracket and followed by any number of them. But this would also match 2 followed by 1, or any of the possible feelings you have there. Now, you can probably imagine why, if you think back to the finite state automata I just introduced earlier, because this would be the finite state automata. You would start off here, and you can open a bracket anytime you want, and you can go over here, and you close the bracket anytime you want. You just keep on going back here, but you have no memory of what you've done before. I could go 100 times over here, and then go to the second state, and I wouldn't know how many times I've gone in the first state. I'm just a little ant following this arrow going like that. So it makes sense that you can't have these parentheses. Luckily, yes?
Sorry, question. Am I right that this picture is not strictly equivalent to the previous regex? Because we need to have at least one closing brace to move to the exception state.
You're true. You're right. Actually, to make it directly equivalent, I needed no movement between the two, so it'd be like an empty movement. I didn't want to go into that this time, so it's not quite, it's actually got a problem with the representation. I'm just hoping that no one will spot it. You spotted it. So yeah, it's not really important to the point at hand, but yeah. So that was the type 3 we just did, the regex, the regular language. Now we look at the context-free languages. What does that mean? Well, that means every other kind of language we can represent using grammar. The big difference between a regex and a regular language and a context-free language is that we can have any number of non-terminals on the right-hand side of our rule, and we can put them wherever we want. So any number of non-terminals. Yeah, and we put them wherever we want, and we can make rules this way. So if we want a matching set of parentheses and a matching set of brackets, we can imagine we have a starting rule S, which can be either A or B or an empty string. A and B are non-terminals, so as soon as we see an A, we can go to the A starting rule, and then we replace that A with parentheses, S, closing parentheses. And then we've got an S again, and we can start again here, and then we can have another A, and we can have as many of these parentheses as we want, and as many of these ones too, because it can be A or B. But at some point we end, and we end up with an empty string in the middle, and it will match any arbitrary number of matching parentheses, where we have this, 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 and this, and now the right-hand side. So that's all fun, that's great, but what has this got to do with making a programming language? What has this got to do with me doing something with Instaparse and getting something quite nice to make a compiler? Well, imagine we have a small programming language, a very small programming language. It only has addition and subtraction. It doesn't even have operator precedence. That's too difficult to think about right now. So what we decided to do is put parentheses around everything. So everything has parentheses around it. If you're Lisp programmers, this should be pretty easy for you. This is our toy language. It's going to be able to compute this as a string. 1 plus 3 minus 2. And for those that are really good at mental mathematics, will know that the value of this is 2. So first of all, we want to know what a number is. At some point, we need a grammar rule which takes something on the left-hand side and returns something on the right-hand side, and one of those things is going to be a number. So the number we define to be any of these. These are all non-terminals, 0 to 9. If we see a number at some point in our grammar, we can replace it with any of these numbers. Now we want addition and subtraction. So an addition we know looks like this. It has a plus sign, and subtraction also has a minus sign, and they've got something on both sides of that. We're going to call those terms, and a term can be a number or it can be something else. So now just remind you, we have a number, 0 to 9, add, subtract, and now we need to define a term. And a term can be a number, or it can be another addition with brackets around it, or subtraction with brackets around it. And that's our entire grammar for our little language. And yeah, those 4 rules should be able to give us a whole language. So what does that mean? Well, take our original string, the one that's going 1 plus 3 minus 2. How would we break this down using this grammar? So we can see there's a parentheses around everything, so it's a term. It's a term that has an add in the middle. That's the top thing, and on On the left-hand side of that add is another term, and that has a number, and that number is 1. And on the right-hand side is a term, which is subtract, and that has 2 terms, and that's a number and a number, and you've created a tree. You've kind of broken up that thing there into a parse tree. And that's all parsing is. It's being able to turn that string there into a tree underneath there, and be able to do something with that tree afterwards. That's the interpreting part. So hopefully you're following along to that, you're getting that. But how do we get that? Yeah, we'll get to that later. So another way of doing that tree is with parentheses. Parentheses look quite familiar, I would imagine, to a few of you here. You will see we have a term, it has an add. The term only has one argument in the add. We have a term here, and has a term over here, and this term has a subtract, and this has 2 arguments, and it's exactly the same as this tree over here, but here we have it in parentheses. The thing you probably notice is there's a lot of the word term around. Actually, we don't really give a shit about this term. Now we've got a grammar, now it's made a thing that's made a parse tree. We need to get rid of the term, so let's look at what it looks like without terms. Now we just have an add and a subtract, and a boxed number, like number 1, number 3, number 2. This is straight. This looks a bit like another set of languages you might have known, and there's reasons for that. So this is our grammar again. What has this got to do with Instaparse? I've just told you how to do a grammar for a language that really doesn't tell you how to make a parser, and I said, oh, look at this string, we can just turn it into a parse tree, but I didn't really give you anything there. Luckily, Instaparse does this for us. So we just need to give it a grammar and a string, and it will give us a parse tree, and it will give it to us in hiccup syntax, that's in vectors, for those that aren't familiar with that. But that's not really typable right now. It's in a form called Backus-Naur form. Like, it's a standard which lets you write grammars out, like a lot of good standards. There's lots of competing ways of doing it that are incompatible. And this is a way of writing it. Actually, it seems that Instaparse is really clever. You can give it pretty much any standard, and it seems to understand them all, including some non-grammar standards that I have not a clue about. But here I decided to say that an arrow is going to be colon equals, so you can see this is the production rule. The non-terminals have quotes around them. This lets Instaparse know that this is going to be something actually in the string, not another rule to look for on the left-hand side. The capitalization is not important, and that's just something I did so I could see it. And we still have the ors. The non-terminals are the same, so a key for that would be this. It's pretty much like, you can see the term versus term, add versus add, subtract versus subtract, and numbers roughly the same, but it's a pain in the ass to write this out by hand, I can tell you. So this gives us a parser. We already had something over here. This goes def 20 parser, and it makes Instaparse. This is the library. We refer it as insta, and then it has a function named parser. Isn't that great? It's so witty. And you have Instaparse, you pass it this string, and it makes you a parser. And it's a record which has a function that you can call on a string. And I call that function on a string. This should give me a nice parse tree. And it looks a bit like this, which is a little bit more verbose than we wanted, but bear with me. So we have a term. Like I said, we have a lot of terms we didn't need, and you can see that it's made these into keywords. They're still the same non-terminal names. This is called a tag, so this is like a leaf of a tree. You can imagine this being a tree, and each leaf has a tag, and that's called the term tag, it's an add tag. And it's also got the non-terminals here, so you can see it's got the minus, it's got the number 3, number 2. Some of these are useful, some of them aren't. So if we look at this, we do care about what the numbers are. Those parts of strings we do want to keep around, but this opening parentheses we don't really care about. This minus, we already know there's going to be a minus because it's got a subtract grammar rule, and it would be great if we could start replacing some of these things. Luckily, Instaparse has a nice way of ignoring a symbol that it generates. And this is wrapping them with these angular brackets, which is a pretty quick and simple way to not have them in a final parser. So we just take all the non-terminals we defined here, 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 and wrap them in brackets. These non-terminals we keep out of angle brackets because we care about the result. We want to know what 0 to 9 is. So yeah, this is all still great. We'll get this thing again, but without those pluses, those minuses, etc. But we still don't have an interpreter. We have a parser. It's making a parse tree, but it's not actually doing any coding. So we need something that transfers this. Now, the Instaparse README, which I heavily recommend reading, is a fantastic introduction to the whole topic, even if you're not doing anything with Instaparse. The Instaparse README says, hey, Clojure has lots of great ways to modify trees and look around. You need to do a depth first search that goes down and takes the bottommost thing and replaces it with this. And I think, yes, I could do that. But I'm a bit lazy. And luckily, Instaparse comes with a special function for me that makes lazy people like me happy. It's called Insta-Transform. It takes a map. This map is of tags. These are the names in here. So we have a tag here, term, subtract, term, number, etc., etc. And it takes a tag and calls a function on the arguments to that tag as if it's a Lisp function. So you have in your vector your tag, so number, for instance, and then you have the string 1, and it calls a function on that string and replaces the value there with the string, with the thing that the function returns. Now that doesn't make so much sense because I talked a bit fast and didn't show you something. So here, imagine we have this tag here, so it's number and 1. We have a function that runs here. It will take a map which has a number entry, and it will have a function, a nonce function, that will then take a string num, which is all the values that come here. It will be function arguments here. So we have the string 1, and to make integer from a string in Clojure is actually really annoying because there's no integer to integer function. You have to use read string. So we use Clojure.edn/read string. It's slightly safer than just evaluating that string, but it doesn't matter. It's from my grammar anyway. Smart Clojure programmers amongst us probably realized that this is not so helpful actually, having a function that passes the value straight to another function. So we could actually just pass that function directly to it. So we have number, and we say, hey, this is the function that's going to translate a number for us. So term does nothing. So we only want to get rid of everything term is doing. So we pass it the identity function. So that means it takes its argument and returns its argument. That means the term is then removed from the values. Add and subtract. Clojure already has functions for adding and subtracting integers. This is pretty good. So we just need to pass it add and subtract, and it should, with these rules, make an entirely working parser. So number reads a string, the term gets rid of the term value with the identity function, the add adds its arguments, and the subtract subtracts its arguments. And we parse those rules with our toy parser, and trust me, I actually ran this in a REPL. I didn't just write this and say, hey, I got a working interpreter. But yeah, this actually works, and we now have a parser for 1 plus 3 minus 2, and all it required were these rules and that grammar you saw earlier. So that is the very basics of Instaparse. That's just touching on the surface. I think I'm just a bit over time, about 3 minutes or so. And I recommend you go check it out. It's a very advanced library. It doesn't struggle, if you know about this thing, it doesn't struggle with ambiguous grammars. It doesn't struggle with left-right versus left-left kind of parsing. It just does it somehow. I've struggled with these compilers in other languages, and I've had these kind of problems. It's very easy to use, and it's worth having a look at. So yeah, and these are my details. If you have any questions. Yes?
Hello, is it possible to run it in reverse? So you've got your parse expression and then define a new grammar for it, sort of take that parse expression and then output.
Not a clue. I think I read something about this. but I don't think it's in there by default.
Should the grammar for the numbers and instead of come to 0 to 9, I'm just wondering what do you do when you also want to have 11 and 12?
Yeah, I decided that this would be version 0.1 of my toy parser. 0.2 actually has multiple digits. You can actually get a lot more advanced than this. You can give it regexes.
Okay.
And you give a regex string and we say we have any number of numbers and that's our non-terminal. There, and then you can start being a lot more advanced and doing more interesting things. That's what I would then do for 0.2, but to keep it within the rules that I put here. Yeah.
Perfect sense for the example. I was just wondering.
Yeah. I foresaw this problem and I know someone will ask about this. Yeah. So yeah.
Thank you. Does it do probabilistic grammar?
I don't think so. It's a formal grammar system. Yeah?
Yeah, I have 2 comments, but I think I'll just do one and then I'll get to you here, because are not actually questions. But well, the first one is just a question. I read your the brief that you guys put on the meetup page before getting here. And I understand that you're working on this in your job, doing something with DSLs. I just wanted to know if you can share with us a little bit about that.
I would love to share it with you, but at the moment it's segfaults.
Okay.
It was something I actually wanted to have as a slide. During our hack weeks, where we get to do whatever we want to work on, which is every 3 months, I worked in the last 2 ones on an alternative to the CMS. We have a custom built CMS in our system, which is very ugly, very difficult for people to use. You have to go into one tab, download some things, take a note on paper of what an ID of something is, and then go to something else, and then take another note. And I said, hey, it would be nice if we had a text interface to this, that we can say, it's an advertising, find a campaign here, pass it to this channel here, and invite this channel to look at this campaign or something. And you could just type that in and say, find channels that started at this date, and that is kind of like a high-level SQL in a way. And that's kind of the thing that I was talking about with new UI patterns. It's pretty similar to, at a previous, I did an internship under a guy working at Skyscanner before, and they had a totally DSL language for querying flights, and it was a similar kind of idea of find an ideal flight by typing in these things, make sure that hours are less than 3, and yeah, etc., etc.
Cool.
In the beginning, you mentioned user interfaces, that it's kind of experimenting, or you think that this gets stuck, or come this presentation to the user interfaces, so what you meant by that?
As I was saying, I didn't go through user interface because I think that's another talk on its own, and we only have 20 minutes, and I already horrendously overran. But I do think that there's a lot to be done on interfaces with this. I would like to play around with that a bit more in other things, and but to do that, you need to have a basic understanding of how to make a grammar. And I think a lot of people find it hard to even get started with this because they didn't do it at university. They haven't done this course, and they think, oh no, making a programming language is so advanced, but it's actually really not. And I wanted to just kind of dispel that before I had any talks about how awesome it is to write DSLs, which, yeah.
But is an interface you mean like input boxes or like?
Yeah, like input boxes,
Yeah.
but they're more advanced input boxes.
And the CMS is not like you.
For instance, Omnibox at the top, like a web terminal that returns graphical things too, you know, like graphs and stuff. I actually have done that, so that was fun. Final questions?
Do you think there's any way to combine this with spec?
Yes, I think there's lots of ways to combine this with spec.